3.1 tangents, and the derivative at a point. The outline of this video is as follows. We will discuss how to move beyond the simple slope of a straight line to define the slope of a curve at a single specific point. This will lead us directly to the formal definition of the derivative of a function at a point, which is the fundamental tool from calculus that allows us to perform this calculation precisely. Once we have this tool, I will show you that it has several powerful interpretations beyond just geometry. For example, the derivative can represent an instantaneous rate of change, like the exact velocity of a falling object at a particular moment. We will see that the slope of a tangent line, the rate of change, and the derivative are all different ways to understand the same core idea. To find the exact slope of a curve at a single point, we can start by calculating an approximate slope using a secant line. A secant line is a line that cuts through a curve at two distinct points. Let us call our point of interest P, and a second, nearby point Q. The horizontal distance between them is a small value we call h. The slope of this secant line is the change in the vertical value divided by the change in the horizontal value, which gives us the formula called the difference quotient, the quantity f of x naught plus h minus f of x naught, all divided by h. Now imagine sliding the point Q along the curve, moving it closer and closer to P. As Q approaches P, the value of h gets smaller, and the slope of our secant line becomes a much better approximation for the slope of the curve right at P. The exact slope of the tangent line is found by taking the limit of this secant slope as h approaches 0. We can now formally define the slope of a curve at a single point, which is a crucial step beyond finding the average slope of a secant line between 2 points. To find the exact slope at a point P, we look at the slope of a secant line that passes through P and a nearby point Q. We then imagine sliding Q along the curve, bringing it closer and closer to P. The slope of the curve is defined as the limit of these secant slopes as the horizontal distance between the points, which we call AH, approaches 0. Mathematically, the slope m is the limit as h approaches 0 of the fraction with f of the quantity x0 plus h minus f of x0 in the numerator and h in the denominator. Once we have this number for the slope, the tangent line is simply the line that goes through our point P with that exact slope. The key idea to remember is that the slope of a tangent line is the limit of the slopes of the secant lines. Let us use our limit definition to find a general formula for the slope of the curve y equals 1 over x at any point A. We begin by setting up the difference quotient for our function, which creates a complex fraction with 1 over the quantity a plus h minus 1 over a, all divided by h. The crucial step is to simplify this expression by combining the terms in the numerator over a common denominator. After some algebra, this gives us negative h in the numerator, which then cancels with the h in the denominator. With that division by 0 problem solved, we can now evaluate the limit by substituting 0 for the remaining h. This gives us our final slope formula, -1 over a squared. For a concrete example, if we want the slope at x equals -1, we calculate -1 divided by the quantity -1 squared, which gives a slope of -1. The key takeaway is that we now have a powerful formula for the slope at any point on this curve. Now we can use our slope formula to work backwards and find the points on the curve that have a specific slope, in this case, -1/4. We start with the general formula for the slope at any point A, which we found to be -1 divided by a squared. To find where the slope is exactly -1/4, we set our formula equal to this value. This gives us the simple algebraic equation -1 over a squared equals -1 over 4. This equation is equivalent to a squared equals 4. And it is important to remember that taking the square root gives two possible solutions. Therefore, we find that a equals 2 and a equals -2 are the two x values where the curve has this specific steepness. This shows how a general slope formula let us locate points on a graph that satisfy a particular geometric property. Now let us interpret our slope formula to understand how the tangent line behaves as we move along the curve. This step is crucial for connecting the algebraic result to the visual geometry of the graph. We found that the slope is m equals -1 over a squared. Since a squared is always positive for any non-zero a, the slope of the tangent line to this curve is always negative. When our point of tangency, a, gets very close to 0, the denominator becomes a tiny positive number, causing the slope to approach negative infinity. Visually, this means the tangent line becomes extremely steep, almost vertical. Conversely, as a gets very large in either the positive or negative direction, the denominator a squared becomes huge, and the slope approaches 0. As an example, a tangent line far from the origin is nearly horizontal. The key takeaway is that the tangent's steepness is directly related to its proximity to the y-axis. Let us formalize the concepts we have been using by giving them their proper mathematical names, which are central to calculus. The expression you see, the fraction f of the quantity x0 plus h minus f of x0, all divided by h, is officially called the difference quotient. This quotient gives the average rate of change of a function over the small interval starting at x0. To find the rate of change at a single instant, we calculate the limit of this quotient as the interval width, h, approaches 0. This resulting limit is so important that it gets its own name, the derivative. For example, the difference quotient gave us the average speed of a falling rock over a fraction of a second, while its limit, the derivative, gives the rock's exact instantaneous speed. The key thing to remember is that the derivative is the limit that transforms an average rate of change into an instantaneous one. We can now give a precise name and definition to the slope of a curve at a single point, and this powerful concept is called the derivative. The derivative of a function f at a point x0, which we write as f prime of x0, is formally defined as the limit of the difference quotient as h approaches 0. That is the limit of the fraction with f of the quantity x0 plus h minus f of x0, in the numerator, all divided by h. This limit provides the exact value for the two key interpretations we have been exploring. Geometrically, the derivative is the slope of the tangent line to the curve at that single point. Physically, it represents the instantaneous rate of change of the function at that same point. For example, the 9.8 meters per second we found for a falling object was its derivative at a specific moment. Remember that the derivative is an instantaneous rate, not an average rate over an interval. In short, the derivative is the precise mathematical tool for finding the slope or rate of change at one specific instant. Let us now use the derivative to find the exact speed of a falling rock at a specific moment, which is a powerful application of this concept. We are looking for the instantaneous rate of change of the position function, f of t equals 4.9 t squared, at the time t equals 1. To do this, we first set up the difference quotient, which represents the average speed over a tiny interval h. This is the fraction with f of the quantity 1 plus h minus f of 1, all divided by h. After substituting our function and simplifying the algebra, this expression becomes 4.9 times the quantity 2 plus h. To find the instantaneous speed, we take the limit as this small time interval h approaches 0. The limit of 4.9 times the quantity 2 plus h is simply 9.8. This means the rock's exact speed at 1 second is 9.8 meters per second, confirming our earlier estimate was correct. Let us pause to see that 4 important ideas we have been discussing are really just different ways of looking at the same fundamental limit. This limit is the one we get from the difference quotient as the interval h approaches 0. Geometrically, this value gives us the slope of the function's graph at a single point, x0, which is identical to the slope of the tangent line at that very point. We can also interpret this limit as the instantaneous rate of change of the function. For example, for a position function, this is the instantaneous velocity at a specific moment. Finally, we give this important limit its own formal name and notation. The derivative, written as f prime of x0. The essential takeaway is that slope, tangent, rate of change, and derivative at a point are all just different names for this single, powerful concept. Let us summarize the central concept we have just explored: the derivative at a point. This single idea unifies several important concepts, from geometry to physics. We began by approximating the slope of a curve using secant lines. By taking the limit as the distance between the points on the secant line goes to 0, we found the exact slope of the tangent line at our point of interest. This specific limit, calculated using the difference quotient, is precisely what we define as the derivative, which we denote as f prime of x0. This gives the derivative a clear geometric meaning as the slope of the tangent, but it also has a physical meaning as the instantaneous rate of change, such as an object's velocity at a single moment. All of these different perspectives, slope, rate of change, and the derivative, refer to the very same fundamental limit. To wrap up, let us check our understanding with two questions that connect the derivative to its two most important interpretations. First, think about how you would write the specific limit that represents the slope for the function f of x equals the square root of x at the point where x equals 9. This question is about applying the formal limit definition to find the slope of a tangent line. The second question asks for a practical interpretation. If a function g of t represents an object's temperature over time, what does it mean if g prime of 10 equals -2? This tests your understanding of the derivative as an instantaneous rate of change, telling us how quickly the temperature is changing at that exact moment. Take a moment to pause and think through your answers, as translating between the math and its meaning is a crucial skill.